Hello, everybody. Welcome to episode 94 of the Hyperthesis podcast. I'm Liam.
I'm Feely. I'm Patrick.
I'm Hamza.
As you can hear, we have a very special guest with us today, Hamza Khattak. Welcome. Thanks for coming.
Hey everyone, thanks for having me.
So, just to quickly introduce our guest, Dr. Hamza Khattak is currently a research associate at MacMaster University, working in the, tell me if I pronounce this right, the Delnoky-Veres lab.
Varesh, yeah.
Varesh, oh sorry, I think I mistyped that here in my notes. The Delnoky-Veres lab. Hamza completed his Bachelor of Science in Chemistry and Physics at Trent University, where he conducted some particularly famous research on why grapes in a microwave oven tend to form plasma, which we'll come to shortly. He also studied how the microwave radiation could be used to drive bouncing and hydrogel beads. Next, he completed his PhD at MacMaster University, where he studied a variety of soft matter systems. In the field of thin films, Hamza studied how soft elastomeric films dissipate energy and the distinct characteristics of gel and elastomer films. He also studied how microdroplets move across fibers, and how that can be used to build a droplet ratchet to pump droplets. Additionally, Hamza also worked on pattern formation in clusters of ferrofluid droplets. And we'll talk about what all this means eventually. But basically, your general process, Hamza, if I'm describing this correctly, groups general processes involving building some apparatus and you poke a system with it. You build some apparatus, poke a system in some new way that maybe people haven't done before, and you see what happens. And then you come up with some simple scaling analysis that explains the physics. I really like that. I always tell people, you poke something and see what happens. Poke it with a stick. I love that. That's kind of what you do in physics. So right now, when you're now that you finished your PhD, you're currently studying how these elastomeric films also form fingering patterns when confined. And I also know that you're pretty interested in kind of scientific outreach, among other things. So Hamza's a man who we'll have a lot of questions for today, I'm sure, and we have a lot to discuss. But before that, I want to get into the intro topic. So today's intro topic is about a paper that I found titled Coupling Nitrogen Vacancy Center Spins in Diamond to Grape Dimer, which was published in December 2024 in the journal Physical Review Applied by scientists from Australia. And I picked this paper because it very much has to do with this kind of, like I say, famous. It's this famous undergraduate research that Hamza conducted that involves grapes and microwaves. So this paper, when I read through it, and it even cites one of your papers. I think the important one. It cites this paper Hamza wrote, which, as far as I'm aware, is an important paper in the field. So I figured this would be a rare opportunity to read a paper that heavily cites an important paper in the field with one of the very authors of that important paper here with us. So that's not something you get to do every day. So I felt like this would be kind of a really nice intro topic. And I'm excited to hear what you have to say about it. But first, before I talk about the paper, a little bit of background. So it was known for a little while that if you place two grapes next to each other in a microwave oven, you can get this hot, bright plasma that forms in between them. There's a lot of really nice YouTube videos of people doing it, some doing it safely, some doing it not so safely, so maybe don't try that at home on your own without doing your research. But this phenomenon was known for a little while, but kind of the physics behind it, or the physical mechanism behind it, wasn't really fully understood, and I believe that's where you and your group at Trent University came in. You came along and did some experiments and kind of built a model for it to figure out how this worked, right?
Yeah, exactly. So actually my supervisor saw the grape sparking when he was an undergrad student. So like it's been around for quite a long time. Is the first thing on it was like before I was born, essentially. So people have been like playing around with it for a while, but no one really like spent research resources figuring out exactly why it's happening. So that's uh sort of where we came in, and my supervisor kind of for undergrads, he's a laser lab. We had a laser lab, like to give undergrads kind of something to get their hands on before they're sort of qualified for the laser. Be like, here, you can work on this great project. So that's how it kind of started.
You can work with the microwave before you get the laser.
Yeah, exactly.
Yeah. So, but during me and Patrick and Feely's undergraduate, we did our degree with a guy, Matt Martell, and he was working on these like micro resonators, which I think is related to this. So one of the main reasons why, like, people might ask, well, why do we care about grapes in a microwave, right? And I think the main kind of purpose is that if you can understand how microwaves behave in these grapes, which are kind of like spheres of water, a pretty good approximation to a sphere of water, you can scale the whole thing down and understand how different radiation behaves in tiny little balls of glass or other materials, these microscopic things, which have really big applications in kind of like sensing technology. And I think that was part of the motivation, right?
Yeah, exactly. There's a lot of research on this sort of essentially superheating. It must have been what the professor, like superheating certain sections of a sample. So you want to heat a tiny bit of a sample. So you have these tiny little metamaterial beads often that you can use at a small scale. But this is sort of that at a very, very large scale. So we're scaling everything up, and we can actually, again, we can poke it. So
yeah, it's much easier to work with bigger things like that than it is to work with these very delicate microspheres, at least from what we saw from our buddy in our undergrad. He never really talked about the great picture, but I think someone from your group or your supervisor came to our university and actually talked about it. We all remember it, but we were talking. We forget the details of who it was or whatnot. But it was they came and it was related to this Matt guy's research, and so we were always kind of interested in this because from when we were young undergrads, people were coming and talking about it to us directly. So if you want, I can describe to you my rough understanding of how plasma forms between two grapes in a microwave, or you can do it. You can tell us.
Sure,
Okay, so you can correct me if I make a mistake. Yeah. But so kind of the mechanism. My rough understanding is that in a microwave, you produce electromagnetic waves, specifically microwaves, and they're emitted inside the oven, and they have about, I don't know, a wavelength of like 10, 12 centimeters, something like that, which is much larger than the size of a grape. So if you've listened to this podcast before, you typically hear me say things like to interact when they're around the same size. I've said that many times, and there's lots of people on YouTube who say that as well. But so a grape's much smaller than 12 centimeters. So how is it that a grape interacts with this microwave radiation? But it has to do with what the grape's made out of, because it turns out that the wavelength of electromagnetic radiation changes depending on the medium it's in. So although the microwaves in the oven are roughly 12 centimeters in wavelength, in water, it turns out that their wavelength is about 10 times smaller. So yeah, and a grape's mostly made out of water. So 10 times 12 centimeters divided by 10 is about 1.2 centimeters, which is about the size of a grape. So the electromagnetic radiation goes into the grape and it interacts with it. And what I'm saying now, I got most of this from a Veritasium YouTube video, which Hamza is actually in. You're describing it to the Veritasium guy, how this all works. It's a YouTube video with 19 million views right now. So we'll ask you about, we'll come back to that because I have questions about that experience.
Just a quick note, that Veritasium video is linked down below in the description, but also in the description is Hamza and Professor Pablo Bianucci, who is the person who came to visit us and gave a talk at St. Francis Xavier. So that's who gave the talk, who was also featured in the video.
Pablo was the sort of the theorist helping us, with these, because we weren't really experienced with these like resonance phenomena. And he was sort of came in with more theory expertise, where we were just kind of like messing around in the lab.
Incredible. I love that. I love a good team of experimentalists and a theorist coming together, come up with a model. So back to the mechanism. So we have grape in a microwave. The 12 centimeter microwave radiation is about 10 times smaller, so it actually interacts with the grape. And what happens is that inside of the grape, the electromagnetic waves become trapped, and they form these so-called resonance modes, which basically means that they kind of become trapped within the grape due to its geometry and due to reflection and refraction, and they take a certain shape within it. And what that does is it causes the grape to heat up in a certain way. So I guess what you might typically expect in something made of water is that when a microwave passes through it, the middle starts heating up first. But due to these resonance modes, the middle heats up, but also kind of the edges start heating up as well of the grape. The boundary of the grape heats up.
So the if you have a very, very large object, right, you're going to expect heating more at the edges because the resonance isn't. But as you get smaller, and it's an individual sphere, then you get more heating at the center. But it's when you bring them together that it starts to heat back at the contact again.
Yeah, exactly. So if you have one grape, so my understanding was that like with one grape, most heating happens in the middle, but you get like a tiny bit around the edge. But as you bring, so if you put two grapes in the microwave now and you bring them closer together, what actually happens is that the heating in the center starts moving towards each other until they happen at the interface. So most of the heating will actually happen when the two grapes touch at the interface between them. And so much heating occurs, it becomes so intense that it actually ionizes the air and the grape around it, and forms a plasma briefly. It makes these like little mini explosions. I don't know if that's a good thing to call it. It's pretty neat how you can just do that in a microwave with two grapes or two, balls of water.
Well, since I'm kind of looking from how I'm not like familiar with this, right? 'Cause I'm wondering if they model the behavior, like the interaction with the grapes, with like a standing wave or something. Because like if it's a resonance, that's why you see those type of behavior.
Yeah, so the one of the analogies we use is a guitar string. You get that's what the kind of a resonance is gonna vibrate depending on where your hand is on the guitar string. So you have these two resonances, and when they come together, they hybridize, and that's why you have the uh, higher intensity at the point of contact. So you have the two resonances interacting with each other.
Yeah, that's one of the very common first year experiment that if you take physics, you do, right? You have the string on this like oscillating stool, and they like mimicking a guitar string. But if you have specific frequency or specific wavelength and specific length of the string, you can have this like stationary wave basically that looks like the note or where the place that they don't move. They don't move in the string. So I'm guessing that there's similar phenomenon is happening.
Yeah, exactly. So actually, you can do an experiment where, so we have a microwave, so we can't really change the frequency. I mean, you can get like, we really bought the microwaves from like Home Depot or whatever, so they're just like commercial microwaves. So we can't actually change the frequency. But what we can do is we can change the size, right? So the sort of control parameter is kind of the ratio of the size of the grape to the frequency or the wavelength of the light. So by changing the size, you can start go off resonance. So as you make it too much larger, you're off that resonance, and you're not going to get the sparking. And then in simulations, you can just change the wavelength and see, okay, as we get to this sort of ideal grape size, we see the intensity increase. And then as you start to go off the grape size, it starts to decrease.
So you must have learned a lot about microwaves during that time. Do you still like when you microwave your food now? Do you still like remember all these details about having to deconstruct and manipulate microwaves and things like that?
Yeah, it's funny. We had like we had to like defeat safety mechanisms and things in the microwaves for some of the experiments. You had to like take the door off and replace it with things or drill holes in it. And like you put like a little mesh so the microwaves aren't leaving the microwave. But like one of our microwaves at home broke. So I'm like, it's probably like some minor issue, and it was just like the door latch thing, and then you're gonna just get a little switch, replace the switch, and then it fixed it. So there's a one practical application of the research.
Yeah, exactly.
I'm just curious, going back to the grapes themselves, and you mentioned the sizes. Was there a difference between green grapes and red grapes?
Yeah, so actually the grapes are kind of essentially balls of water. So we actually did a bunch of we did like different fruits. So we did grapes, we did um, cherries are a bit large, but they get close. Gooseberries work quite well. I don't know if you've had gooseberries before.
Yeah.
They're kind of very tart. They're quite tasty fruit. They work. Once we like sort of had sort of the fruit part of it, we moved to hydrogel beads, which are essentially just the polymer that absorbs a bunch of water, and it's essentially 99% water, and it still works in that. You have to put a bit of salt so there's something to ionize, but even with just balls of water, it works.
That's I think that's the first time I've ever heard anyone mention gooseberries besides like my grandmother when I was a kid, because she had a little gooseberry bush in her yard, and then I never heard of them again until I don't know, like a few months ago I saw some at the grocery store and I was like, holy, I haven't seen those in a long time. Because they're like little, they're smaller, way smaller than grapes though, right? Like they're
And also, like, if you play the video game The Witcher series, there's lilac and gooseberries mentioned quite often. So that's how I learned it from, actually.
yeah, I learned a lot from video games as a kid, but we're derailing here a little bit, I think.
Yeah, we had to expense the gooseberries. So it's funny, like these are research gooseberries.
Yeah, fill in your reimbursement form. Oh yeah, I guess you had to like get your grapes reimbursed and stuff, or put those on the expenses. That's pretty cheap though for something like a microwave and grapes. Like it makes a lot of sense why you would study that, because I imagine paying and financing like these little microspheres and creating them is a whole ordeal when you can just spend like $100 or so on a microwave and a bunch of go out and get grapes from the grocery store whenever you need them. Like very practical way to do. There's a good reason why you're doing it instead of working first things first with the little microspheres.
Also, is there a term that you just use to describe like scrapes, like in scientific term, or just call it grape, or you just call it like bounded water, spherically bounded water or something?
Yeah, just balls of water. It's pretty much for our purposes, they're just balls of water.
Well, this paper. So coming back to this paper for the intro topic, I just want to get some background out of the way. But this paper just calls them like the grape or grapes. I think it might call them like the balls of water sometimes, but it quite often I think just calls the ball of water a grape.
Okay, because I think sometimes scientists we like to use certain fancy words or fluff it up a little bit, and it's like, well, I'm glad it's just used very direct. It's grapes.
Yeah, exactly. Like we tried to make the like paper very approachable in terms of like, and this should be true for any research, but especially for this one, we like made sure like we're not using too fancy terminology. Like anyone should be able to read it and understand it.
Yes,
Exactly.
we gotta tell that more to the string theorists and all these fundamental physicists.
Even the people I read my papers from, it's like sometimes you read them and it's just like, oh dear God, like who wrote this? You can tell that they've been in academia for 60 years or so because they've lost touch with reality, and I'm sure I'll do that one day too, but I'll try not to at least. But anyway, back to this paper. So, what did this paper do different? They studied grapes in microwaves, but what is different from what you did and what other people have done since? This paper claims that your previous work, Hamza, and among other people's previous work, focuses more on the electrical field within the grapes and how they contribute to the formation of plasma. But this paper builds upon this previous work and shows that the grape pears can also enhance magnetic fields, which, if you ask me from an outsider, that seems, of course it would. If it enhances the electric fields, it should do the magnetic fields as well. But I guess they went and kind of did the experiments and simulations and whatnot. So they say that their study not only validates previous work on understanding grape dimer resonator geometries, but it also opens up another avenue for exploring alternative microwave resonator designs for quantum technologies. So they talk about the magnetic field aspect, which previous literature did not do as much, I guess. Specifically, this team of scientists from Australia, they used these special nanodiamonds that contain nitrogen vacancy center atomic scale defects, which I'm not 100% sure what that means. I have a rough idea, but basically they use these nanodiamonds, to act as kind of with defects, and these little defects kind of made them behave as little tiny magnets so that they could detect magnetic fields. Other than that, the experimental details were beyond me, but somehow they use these little nanodiamonds as little magnet detectors in order to determine how the magnetic fields resonate within the grapes and help contribute to the plasma.
So one of the interesting parts is, so we can sort of measure with our experiments, we would measure sort of intensities of fields, right? So if it heats something, that means the electromagnetic field intensity there is high. But I think with their technique, they can also measure. I just read this last night, but they can measure directionality. So we couldn't actually measure we're not really measuring field. We're measuring, like if you're measuring, you're measuring the kind of effect of the field, but they're measuring the field directly, which is that was quite interesting. And the sort of indirect method of you're going from there's a fluorescence going on, there's microwave, there's a coupling, and then it's always fun to see these sort of tricks of making these measurements.
Yeah, it's one of the nice things about the process, I guess, right? Is everyone, I don't want to say they start with the easier thing necessarily, but people will start with the more face value stuff, and then other people will come along and start digging into it deeper, and it's it's how science works, I guess. But so basically, what the end result of this paper, what they found, at least that's what it says in their abstract somewhere, is that they found that the magnetic field of the microwave radiation becomes twice as strong when the grapes are added to the microwave. So it does what you would expect. It does this resonator thing and creates plasma. So I thought this was kind of, I just wanted to get your thoughts on the paper. I mean, you read it quite quickly. I did as well. But yeah, you just said you thought it was kind of neat how they did this, and
yeah, it's fun how they must have bought a lot of grapes, because the amount of precision they had on the size of the grapes was very high. It's just like we have the grapes are exactly this dimension by this dimension. They only use grapes of this particular. So they did the experiment very, very nicely, even just using grapes, because we're like kind of got with the grapes you can't control the size that well, was our thought. And then we just use hydrogel beads because it's like exactly, you just be like, I want this size, and you get that size. But it's interesting they're able to do that with the grapes and directly measure the field.
Maybe they use wine grapes. They're a bit more spherical, and I find they're more consistent than the grapes you get to eat at a grocery store. Maybe, who knows?
We didn't have the right grape supplier.
Yeah, they were giving you all the leftover ones or something. But yeah, so that's kind of like a little window into what Hamza did as an undergrad. I think we'll come back and talk about it a bit more later. I have many more questions about kind of not so much the science behind it, but other things. But yeah, I just thought it'd be interesting to talk about a paper that cited you, which again, I think I'll ask more questions about later. But anyway, that was the intro topic. So now we can transition to the main topic, which is not about your past research, Hamza, but will be more so about your current research and kind of what got you into physics and stuff. So I guess to start, what do you do now?
Yeah, so we study soft matter systems pretty broadly. Uh, so there isn't a specific kind of, this is I study this sort of system, but it's kind of soft, and we just kind of mess around, see what's interesting. So like my, I don't know how, March meeting, I don't know how many of you go to March meeting, like if a big American Physical Society.
Yeah, I went there a while ago when it was in Vegas, I think, a couple years ago, maybe more than
Yeah,
a couple.
I always hear about it, but I've never gone.
Oh, you're not really in condensed matter, so it's mainly a lot of condensed matter.
Yeah,
There's like
well,
April meeting and all the stuff for auto fields.
depends who you ask, because I do condense matter, but it's like Bose-Einstein condensate. So
This year they're combining it. March and April are together now.
Oh, okay.
oh, okay.
Anyway, I try to have try to do a completely like the March meeting talk from last year is pretty much completely unrelated to what the March meeting talk I'm giving this year. So I really like jumping around, just sort of kind of get things started, and then just like this paper's this work's done, and then just like I want to do something completely different.
I guess for the background, could you explain what you mean by soft matter?
And so yeah, soft matter is squishy things. So essentially, if you can apply force and easily deform it, and so again, this is very like what does easily deform mean? It's a bit nebulous, but uh, essentially, if you can apply a small force and easy deform it, that's soft matter.
Yeah, I think there's like a wide range of things that you could consider soft matter, right? Like, I guess maybe like I don't want to say like sand. It's sand's a weird one, but sand is like maybe soft matter and Jello, or like like a could you call like a pillow soft matter? I don't know. It's really like there's so many different kind of subdivisions of it. I feel like, and each one probably comes with their own interesting things.
Yeah, exactly. Which is good, nice for us because then we can just like look at something interesting and be like, okay, we're studying this now. So it's like you talked about sand, so there's a lot of interest in these granular systems. So like some of the other uh, researchers in our lab are studying these sort of like analogs to this sand with these microdroplets. So we try to like just like see what's interesting and study that.
Okay, so you work on a whole bunch of different things, which I really like. I tend to hop around a little bit, um, as well. Maybe not as much as you, but I try to. I don't like sitting on one thing for too long. But so you work on a bunch of different things, but is there any particular thing you're excited about right now that you're doing? Maybe that's different than what you worked on during your PhD. Like the thing you might want to talk about at March meeting. Maybe I don't know if you don't want to give it away yet, but
I guess I'll be giving it away in a couple months anyway. So so the what thing we're studying is it's funny because you put at the March meeting abstract, like you have to submit it in like October or something, right?
oh, that's
So,
brutal.
but at that point, like I mean, I didn't really have anything. So we're just like kind of like give something somewhat generic and then like, figure something out. So I think at this point it's pretty set is going to be, so when you stretch, uh, actually, when you stretch something, right, there's some tension in it. Now, if you apply another material onto it attached to it that's not stretchy, what's going to happen is uh, those tensile forces is going to start to, and you release those forces, it's going to start to curl up the material, right? So you imagine like two materials of different expansion coefficients, for example. So like I don't know bimetallic strips. I don't know if people, yeah. So if you have a bimetallic strip, one end expands more than the other end, and it curves, right? So we're trying to sort of do that, but with polymeric materials.
Just for people listening who may not be familiar with bimetallic strips, if you've ever seen a temperature gauge that looks like a clock, that has bimetallic strips in it, where they expand differently at at the same temperature. So it kind of twists this dial that will tell you the temperature. So if you've seen those, then you've seen an example of bimetallic strips at work.
Or if you have seen swords that curve, right? Because there are two different type of metals or different composition of metal in there. That's how they make it curve. Because when you heat it up, they don't expand at the same rate. So you get this curved blade, which is pretty fascinating how people figured that out thousands of years ago.
And one final cool thing is in kettles. Once they're designed that once they reach a certain temperature, they'll shut off because of that bimetallic strip bending to a certain point.
Okay, I guess I'm the only one here who's never heard of them. But that was a nice little intro to them. Okay, so you're working on biometallic strips, but kind of like instead of that they're made of like polymers or things like that.
So it's actually so we take a latex sheet, and so there's two ways we can do it. So first, you want to kind of study the processor. You want to start a simple model for what's going on, and then you can kind of apply it a bit. So the simple model is you take this latex sheet and cut it into a tiny little strip. So it's essentially reducing the dimension. So you have like a 1D system. Then you stretch it. And then if you apply some hard material on top of it and then unstretch the latex, you'd expect it to curl up, right? Because the one side wants to retract, it's under tension, and then the other side wants to stay. So it's gonna want to curl up like the bimetallic strip. Right? So that's in 1D, that's what we expect to happen. But what we're doing is using a UV curable resin as so there's latex on one side and then a UV curable resin on the other side. So now if you have this UV curable resin, you can apply it. So the application process is a bit of, take a tiny little micropipette and kind of slide it along your UV resin along the strip. And then what you can do is, it only cures if you apply UV light to it, right? So what you can do is, say you cure one section, that section is going to curl up. You don't cure the other section, that won't curl up. Now you release the tension, right? Now that uncurled section, the section that wasn't cured, is going to be kind of straight and kind of hanging down. And then you cure it afterwards. So now you have a straight section and then a curled section. So try to sort of play with this differential curing to sort of create these different geometries in these materials. And then once you have it in 1D, what you can do is think about, okay, well, we have 1D. What if we have a sheet of this latex material? What if you stretch the sheet? So you can stretch a sheet, kind of print a pattern onto it with the UV curable resin, and then get it to like fold up into all sorts of fun shapes. And then you don't have to cure the whole thing, so you can get it to fold into like a cylinder, and then kind of like glue the cylinder together with another curing step.
When you model these things in the theory part, is this more like a classical, kind of like classical spring? So I know like rubber band, you can use statistical mechanics as by equation of state and do the entropically.
Yeah, so yeah, actually, last semester taught the intro soft matter course, like the third year soft matter course at our MacMaster. So yeah, the rubber it has very different behavior from a normal spring, right? Because you don't even have, like, normally if you have a spring at small displacements, it's linear, right? You apply more force and there's a linear increase in the stretch. But you actually get, with a macroscopic piece of rubber, you actually get a slightly different behavior. So yeah, the rubber does behave differently, but for our purposes, it's just like you're applying some stretch to it. There's going to be some tension, and that's gonna, I mean, we haven't come up with a theory yet, so we'll see what that's gonna look like, but we'll come up with a theory later.
Exactly.
Okay, I think because I think you're talking to Liam and I, we do kind of theory-ish. Oh, he's doing theory, I do computational stuff, which I believe should be his own thing. But we're grouped with theory, right? And it's so strange to hear, like, when you do experiment where, oh yeah, we we'll figure out theory later, and results come first. And to me, it's like, whoa, I have never done that. So I don't even do the experiment at all. It's like, well, here's a theory. It should look like. We have no idea when you do experiment what it should look like. So are you doing everything like so far, like in your career, is all experimental work?
Yeah, for the most part, I've been like we do like sort of scaling theories, but for the most part, I've been doing like essentially we do some experiment, try to poke the system in a weird way and try to make it do things it doesn't want to do, and then once we do that, then maybe theory.
Yeah, the experimentalists love scaling exponents and how things scale. That's one thing I've learned because I do theory, but I try and do a decent amount of it with like the experimentalists in mind. I say like, okay, if I'm have this BEC, bose-Einstein condensate, and I do stuff to it, how do things scale? Because that's what the experimentalists will measure in an experiment. So that's pretty much what a lot of experimentalists do. Some of them will work with theorists for things like you did with the grapes, but a lot of the time theorists are slow, so they'll just go do an experiment, measure some scaling, and then a theorist comes later and proposes a model and see if it matches that. Um,
Well, so you said scaling, and when I hear scaling, one thing that comes to mind was the renormalization group. 'Cause I think it's directly with scaling. Do you do anything with that at all? I don't think it's very experimentally thing. It's not really experiment wise, but
uh,
like you have to deal with it.
So our scaling is like y is proportional to x to the n, and we try to figure out a simple model why n is 2, like why must n be 2 or whatever. So it's yeah, the mathematics is very simple. It's just sort of unit analysis type, just like kind of getting the fundamental building blocks of the system.
yeah, I don't even do renormalization group. The only people I know who do that are like the hardcore mathematical physicists at MacMaster. Yeah, like scaling is like, I guess in my system, like you trap a gas. Imagine you trap a gas. You release it and let it expand. Like, how does its amplitude scale with time? Does it scale like a square root, or does it scale like a cubic, like t to the 1/3, like things like that? Um, not no intense theory. Well, maybe if you want to derive a theory for it, but
I guess it's a different word for scaling in my head, or different meaning, because when I hear scale, I mean like when you go from microscopic to macroscopic or something like that. But I think you remain in the same scale. Study how the scaling in that scale work.
yeah, there's so many different languages in science. I probably for me the hardest part of it is like I read someone else's paper and they're doing the same thing I'm doing maybe, but the way they describe it is so different. It takes like a few days to figure out what's going on. It's very interesting how that can happen. Um,
If you
oh,
like
sorry.
hop around from field to field, like I don't really have any idea of what's going on in this. Like I've not worked with this system. I don't know what's going on. So I like being in a place where I don't really know what's going on, and then slowly figuring out what's happening.
It's a good way to learn. So part of I guess there's probably I mean I can't think I'm not in this field, but I'm sure there's a lot of applications of to why you're doing these kind of this system with this UV activated resin and with polymers instead of the regular macroscopic. I'm not trying to. I don't know how to ask what I'm trying to ask, but I'm sure there's lots of applications for it. Um,
Yeah. So I mean, we talk about in the lab about like we do it because it's fun, and then the applications kind of just sort of organically uh, come out. So just try to poke the system in fun ways, and the applications will come up. But I mean, you have to justify. I mean, we're getting funding, so you have to justify it. So the way, like for this system, for example, uh, if you're 3D printing a material, like so 3D additive manufacturing is sort of fastly growing field. 3D printing, there's lots of different ways of doing it. But when you're 3D printing a material, usually it's fairly stiff materials. You can print softer materials, but the idea of this two-stage, you have a very, very elastic latex material, and then you can maybe form it around, print it like forms around. So for example, in a wearable, kind of like wraps around someone's arm, and then you can essentially do a gluing step later with just applying UV. So you can think of it sort of in these manufacturing these new materials, we can have separate out different steps of the shaping.
So there is a keyword I found that I think you might be able to explain better. What do you mean by elastomeric material?
Yeah, so elastomeric. So you have these polymer chains, and they're kind of linked together so that when you stretch them, they return back to their original state. It's pretty much the idea of elastomeric. And I mentioned gel materials in contrast to elastomeric. So like a rubber band would be an elastomeric material. A gel is when you have these, this big crossing network where you stretch and it comes back. But with the gel, you also add some uncrossing chains. You add things that are kind of just like free floating around in there. So that's sort of the contrast between a gel, which has this network, but also free floating chains, whereas a pure elastomer would just be this big network of polymers that stretch.
Okay, is there a difference between, like, let's say if the colloquially we say elastic, when even that description, like, oh, something that deforms come back to its natural state, it seems like elastic.
Yeah, so I guess in our field, elastomeric usually refers to polymer type materials. I mean, yeah, they are like on a small length scale, pretty much everything is elastic. But for example, you can't stretch a metal, twice its original length and then expect it to return back. So you do get larger possible deformations with a lot of these elastomeric materials. But for us, or at least for me, I kind of define it as these polymer sort of systems rather than, so it can be an elastomeric material is elastic, but not all materials that behave elastically at certain length scales, I would call.
So kind of pivoting a little bit before we ask you about your PhD and things like that. You're currently a research associate, and you mentioned that you taught a class. So the three of us are, well, maybe we'll complete our PhD soon. That's the goal. But um, we're kind of a year or so, maybe a couple years behind you in our career path. So we're interested probably in, like, what is a research associate? How did you go about that? What do you do now? Yeah.
Yeah. So it's just going to depend, even similar to the PhD where your supervisor, like it depends a lot on where your supervisor is, where you're working, things like that. It's such a ill-defined position, like postdoc research associate, that wherever you go, it's going to be quite different. So if you go to one place versus another place, your job description is going to be quite different.
Hmm.
At least for me, it sort of, so my supervisor, Kari, the way it's working with him is I sort of, before I was more focused on sort of my own projects, whereas now I have a lot more responsibilities in terms of managing. So I would have students in that case as well, but I have more responsibilities in terms of managing other students, managing lab things than I did during my PhD. So now, like grad students as well, I'd be.
And you taught a class. Is that something you're expected to do, or is that kind of like you volunteered for, or like maybe not volunteered, but like it's part of your job? I guess, is it like expected, or is it part of your job but only sometimes?
I had the choice whether I wanted to teach a class or not, and that would be a good experience. And it's the course that my supervisor taught the year before. So it was not too much of a, like, it's still like if you have 3 hours of lecture a week, you still have like more than double that in terms of like prep and all that. But the actual lecture content was already made, so it helped a lot in terms of I was kind of following what was previously set up. But it was really good to you know get that experience and try to hopefully teach the students something about
Yeah.
self-minded physics.
I've never taught a class before. I know some people teach classes during their PhD. Um, occasionally. Like we have a friend, Grace at Waterloo. I think she taught like a stat mech, or sorry, not stat mech, like a statistics class before she graduated from her PhD. But the closest thing I've done was I taught my supervisor's fourth year quantum class for a week while he was on vacation or something. And I remember, like, even just for that 1 week, it was like quite a bit of work. Um, so balancing research and teaching when you're a prof or when you're a research associate or maybe even a postdoc, like that's a learning curve, I think.
Yeah, one thing that I think I was thinking about that too because there's some opportunities here. But what I was advised is that well, if you want to get your research done, you better not because it's actually a lot of work to do all this stuff. And while you try to finish, or why it depends on what's your progress in your research and where you are in your graduate program, it might not be the best idea to do because I think people underestimate how much work that is to teach a course. And what if you have to come up with all the assignments, the exams, grading? You can have TAs, and sometimes if you're teaching third and fourth year courses or graduate courses, different story, right? But the upper year advanced classes, it can be quite taxing if you want to try to complete your program. And it's not really necessary also for your resume per se, because most of the I find like, well, most of the jobs don't really require that, especially for postdoctorate. I don't have experience on that, but they don't seem to care so much about the teaching part for most of them. I think they care more about your research. Is that true?
Yeah, I think it seems to be true that they're more focused on research than teaching. For me, I'm eventually trying to go to industry. I just kind of want to have as much fun in the academia as I can, and I've always wanted to uh, teach a course. So
I think when you try to apply to be a professor opposed to like a research associate or a postdoc, I think teaching experience matters more then. It's still, I mean, maybe I shouldn't divulge McMaster's secrets, but Hamza and I were on a hiring committee once or twice before, and they have like these rubrics of how much they care about what you've done. So there was like 50% of their score comes from their research, and 30% comes from their teaching experience, and 20% comes from EDI and outreach and things like that. Like those aren't the exact numbers, but they care more about research. But for a prof, they do care about teaching, but maybe not as much.
Well, Liam, I'm gonna say this, right? Our former supervisor, when I went back to give a talk a few months ago, said something very differently. I think he was like, well, nope, it doesn't matter. I might say it matter. It doesn't matter because what really practically, if you're working at your university, you want to bring research funds, you want to bring money, and teaching is not exactly that's significant.
I
But
think it
that's a
depends.
topic for another day. It depends. If you go to liberal arts college, maybe.
No, I think it depends on the university and the department and things like that.
yeah, I think also what they say in terms of what they value versus what they actually value may not be.
Yeah, on paper they value it, but does the committee really value it, right? Um, so yeah, research is definitely the focus when you hire. But anyway, so it's okay. That's some good insight into that kind of stuff.
So I got a question more on the interest. So what got you interested in this soft matter stuff? Because I think experimentally there's so much to do in the realm of like condensed matter physics, right? And are you not trying to do any fluids at all? Because I think most of the soft matter are pretty much in a solid state.
So we do. So for example, one of my projects was on making these micro droplets move across fibers. So there's quite a bit of fluids in that. In terms of why I got into soft matter versus into another, I mean, I feel like I have fun doing a bunch of different things. So I don't think I would have any, like, if I went to hard condensed matter instead of soft matter, I don't think it would have made like it was fun to study. I kind of started on some soft matter projects and I really enjoyed them, so I kind of continued on. But I don't think it would have made much difference to me if I was studying soft matter. Even like doesn't even have to be physics. Like I've worked on chemistry projects that are a lot of fun, so I've kind of just like working around playing with things.
Seems like a type of man who like to tinker around,
Yeah.
Okay, so you poke around, but physics allow you to do that in a very specific way, too, right? And it's a very, in a sense, sometimes rigorous way. There's very specific protocol. We have to, you can't just poke something. You have to control variables. Science do that in general. So I think it might be, so it's not like you're interested in the, well, okay, let me put it carefully. So your interest is more on the process, not the actual subject matter. Is that more accurate description?
I mean, generally, I'm still interested, of course, still interested in the subject matter, but I definitely like the process of doing science or even, engineering, just building things like that. Whatever specifically I'm studying is, I mean, some things I may enjoy more than others, but the process is what I really love.
Yeah, the problem solving aspect of it.
I'm just gonna say I agree with you. That's the fun of experimental stuff, is that you get to problem solve in real time and you get to see the results of fixing those problems, whether it's like something like a leak or figuring out how to adjust something, or even through code, just trying to figure out, okay, how do we get the result that we're actually supposed to get? So lots of cool problem solving that you have to do.
My version of that is like I do something and find some experimental paper where my something matches their something, and I'm like, yeah, my real time validation.
Yeah,
I
I
mean,
was curious about. Oh, sorry. Go ahead.
I mean, the skills we developed is, I think when you do a very specific field, I used to think like, oh, I'm just solving this specific problem, and I learn more about this specific subject matter. But really, the skills we learn is like how to do science, how to do physics, and at the end of the day, you're not gonna work on that project forever. So you have to move on to other things, and learning the skills that translate is pretty vital to our work.
So speaking of moving in between projects, going back a little bit to your PhD, so were there any particular projects there that you like in your thesis, for example? What were kind of like the big projects you worked on there, or the big project?
So again, the PhD was also kind of hopping around. So we did like so there's the thin film deformation stuff. We also talk about the barefluid droplets, which is a fun project. So we create these clusters of monodispersed ferrofluid droplets. So we create these droplets are, little iron nanoparticles in them. So like if you apply a magnetic field between two of them, they're gonna parallel magnetic field, they're gonna repel each other. So what we can do is we can make these tiny little droplets and collect them at a meniscus. So we have this meniscus. So now all these, because of the gravitational force, these droplets are forced into contact with each other, right? We put them into some water, they're oil-based, so they float up into this meniscus, and now they're collected with this meniscus. So there's this kind of restoring potential, keeping them in this cluster. And then what we do is this water is actually a solution with surfactant. So the surfactant makes the droplets stick to each other on a short length scale. So on a short length scale, these droplets stick to each other. And then now as we start to apply the magnetic force, now that is a repulsive force. So as we apply the magnetic force, that force has to sort of compete with the attractive force from the surfactant. And there's going to be some sort of balance. And then you can get these fun patterns forming, these little strings. And then you get these transitions, but depending on how sticky they are versus how strong the magnetic field you apply is. So that was one of the projects during my PhD that was fun to work on. Again, a lot of fun building and
Yeah, you get a lot of that kind of stuff in my field as well, where again, completely different, but you're basically like looking at phase transitions between, there's some force, there's like a short range repulsive force between particles or a long range attractive force, and you tune them and you see like where do they balance and what happens. And I'm always really interested in that kind of stuff too. Okay.
yeah,
Okay.
and the phase, looking at the phase transitions for sure. I mean, it's not that sharp, but you do get these where we're in this sort of compact phase versus string like versus a dispersed phase, and you can ramp up the field to go between the phases.
And then someone later can come and find an application for it.
Are these patterns like come from symmetry, or are there specific patterns? Like where do these pattern emerges from? Like are they like do you predict what pattern it would make, or do you know what pattern it would make, or are these things that they just discovered?
And we were talking earlier about the visual part of science. It's a bit hard to get across on the podcast, but the patterning depends on. So if you have it's essentially how far apart you can get these particles from each other, right? So if you have them completely clustered, you're maximizing the number of contacts. You're minimizing that attractive interaction. But if you imagine having a very long string, right? You're separating a lot of droplets from each other, but without breaking too many bonds. You still have bonds between them. So that's why the sort of intermediate phase is kind of string-like, because you can have this distance between particles from the magnet, but while still having a bunch of contacts. So that's where you get the string phase, and then eventually, if you have too much field, everything just separates.
Okay. And I think what Liam mentioned before, or was in the text, is the fingering patterns. What does that mean? Is it like interwoven fingers? Like,
So the fingering pattern is a different project.
okay.
Yeah. So
Yeah.
this is it's a different project. The fingering patterns. It's actually in that system you have a lens, so like a hard lens. So and then you place it against an elastomeric material, and then the elastomer wants to contact the lens, but to do that it has to stretch. So there's a balance between it stretching to contact the lens. So it's on the surface trying to contact the lens, so that requires some, there's some force required to stretch it. But that also gains energy in terms of you have the contact is energetically favorable. So the balance between those creates these fingering patterns.
Okay, so you're talking about like a convex lens being pressed onto the film.
Yeah. So yeah, it's just very very different system from the ferrofluid stuff. Yeah.
Okay. And that's not a pattern of light, it's a pattern of deformation?
Yeah, so you can see you can measure it optically, but yeah, it's a pattern of deformation in the elastomer substrate. So you have some parts that go up, and there's volume conservation, right? So it's the parts have to go down, and then you get these fingering patterns.
I'm
I see.
thinking-
Because I'm probably thinking of the same thing. It's like maybe because I think of lens and material, I think of Newton's rings, they're like those type of optical pattern. But you're saying it is more like a material pattern, so it's not optical pattern.
Yeah, exactly. It's a actual material physically moved, like deformed.
Okay.
I'm thinking for every episode we release, we do a little like social media Instagram post. So I'm thinking maybe I'll find some of these photos from the papers and, of course, cite them or whatever, but maybe post a few of these photos along with the episodes, or the episode post, so that people can go look at them if they want to.
Yeah, to me, fingering pattern is I have used it in different cases. Like you played string instrument, violin, guitar. That's fingering patterns, right? I'm pretty sure in any woodwind and all this stuff there might be too. So I'm so confused. Like, what does it mean by fingering patterns?
I think of this thing called branched flow, which is, I think, completely different. It's like you get like this natural focusing stuff that happens anyway.
Yeah, so the branched, it does kind of look like little branches sometimes when you have the patterns coming out. So maybe it's somehow somewhere deep in the physics there's some relation.
Yeah,
between
that's
those.
something my supervisor would be interested in, because you went to his talk the other day. I saw you there. I think I was right behind you, but he's very interested in like universality and seeing things in all these different places and stuff like that.
Actually, I was going to talk about the caustic. So when your supervisor, like it's really cool, caustic patterns and combining it with other things. But for the grapes, right, the grapes are pretty much opaque, right? You can't see, well, they're opaque enough that we can't see. But if you have the hydrogel spheres, now if there's a spark between them, right, there's going to be a bunch of light, right? And then the light forms these really nice patterns in the hydrogel sphere, so you can see these light patterns on the other side. So you get these caustic patterns, which is really fun to see in
Yeah,
the
the
hydrogel beads in the microwave. So
cost.
if you're looking for photos to post, maybe one.
Oh yeah, that's a good one actually. I'll have to talk to you about that. I anything with a caustic, which they appear everywhere, man. Like it's wild. I see caustics everywhere where I go. It's cursed now.
Liam, if you're a hammer, everything you see is a nail.
Exactly. Exactly.
I mean, like, we have so much light out in daily life. Like, it's caused the human natural focusing of light. Like, it doesn't seem so difficult to have, isn't
Yeah,
it?
but you
If
see
you
it
have any
in
refraction.
no, but you see it everywhere, not just in like light, but in other systems that aren't light based, and it's because yeah, it's because focusing can only have certain shapes. We've talked about this a million times.
Yeah,
But
any wave base, in the ocean or whatever, like any
yeah,
waves, right? And then, you can be two things, particles or waves. So,
Yeah, it's similar to like it's squishy things. So you come across squishy things and weird soft matter deformations everywhere in everyday life, fluid dynamics. So it's a similar thing where you see a lot of nails as a hammer.
yeah, I mean, I study crystals, and most things are crystalline, have crystalline structures, and they're very interesting. But at some point, it's like, well, we are studying physics, which is nature, and if you don't see it in nature, I think you're studying super fundamental stuff, or just something very far away, right? And fortunately, I think almost everyone here studies something that's somewhat relatable to daily life. Then argument is more the physics have the progresses. More physics progress, the less relatable it is to daily life, right? Imagine Newton's closer to daily life, and now you will study trying to find some dark matter which have like no relation to daily life at all. Well, some dark matter physicists might disagree, but I think it's pretty much
Yeah. Well, one of the reasons that I was not that interested in studying astronomy is because you can't poke it. Can't poke. But maybe in some 1,000 years there's some kind of new technology or new probes that allow us to poke things more easily. But for now, one of the nice parts of soft matter is very easy to poke,
I see.
both figuratively and literally.
so can you talk about this micro droplet fiber thing that you used to build a droplet ratchet? You just I know you have so many projects. I'm not going to get you to describe every single one of them, but I kind of want to hear what a droplet ratchet is.
So yeah, if you have um two fiber, I'm so used to like doing things visually. I'm putting my hands up here, but if you have two fibers and you hold them at an angle relative to each other, the it's energetically favorable for the droplet to move towards the apex.
So you have so sorry, you have two fibers. I'm not imagining just two like wires, and you have like a water droplet suspended between them or something like that. Yeah, yeah. So
Yeah, so yeah, you have two fibers and you have some kind of droplet suspended between them. If the droplets if the fibers are far away, the fibers at an angle, right? So if they're far away from each other, the droplets will deform and kind of stretch out to fit between them. So it's energetically favorable for it to start to move towards the apex of the fibers, right? So if wherever they're kind of closer touching, so that there's this sort of motion towards the apex. So the first step is, again, you want to develop a scaling model to simply quantify what are kind of the physics behind this. So there's like the surface tension kind of pulling it towards the apex, and the viscosity kind of slowing it down. So that's sort of the fundamental fluid dynamics of what's happening. And then once we have a good understanding of that, we can start to play around with how we deal with that system. So if you have two straight fibers, eventually they're just going to reach the apex and they're going to stop, right? But what happens if we have, instead of two straight fibers, if we put a bunch of zigzags in one of the fibers, right? So if you have a zigzag in a fiber, it's going to reach one point on the zigzag where the straight fiber and the zigzag are close together. right? So now you're stuck there. It's not going to go in either direction because you're at the point of the zigzag. But what happens now if you translate the straight fiber to the other side of the zigzag fiber? Now, instead of being at point of, you know, they're at the sort of apex, now they're at as far apart as they could be. And if you just give it a little push, you can start to move it back, moving forward. So then you can repeat the sort of process and kind of use the zigzag pattern to flow a droplet across a distance.
Okay.
I understand now why you say, well, it's difficult without the visuals. Like these are very visual things. Like, wow, it's really hard to explain, isn't it? I was like trying to picture it in my head, like, wow, this is difficult.
I think I get it. Okay. So what was the motivation behind the zigzags? Did you have like, was there any intuition why to use that, or was it like an accident? You just had like a bent fiber or something, or
This was like, so you need some kind of like bit of flair at the end of your project to kind of, make it more attractive to journals and things. And this was like,
yeah.
what can we do? People like moving things across large distances. So let's see if we can do a little zigzag. Well, not a zigzag, like, wait, how do we move? Because like the apex ends, how do we change the system such that we can move across a large distance, right? Because the geometry is such that if you just have one angle, your droplet has a certain size. It can't be like stretching an infinite amount. So to move a large distance, you need, and then came up with the zigzag somehow. And then we had to like actually, these are little glass fibers, and they're, the diameter of the fiber is maybe like 50 microns or so, something like that. So we have to like make a zigzag pattern in a glass fiber.
Not very easy, I imagine.
Yeah. We have like a little, essentially just like a really hot platinum wire, and then you can grab one end and like kind of push it down. You just essentially not melting, but like softening the glass and making the zigzag.
So it sounds like you use a lot of instruments. So how much of your work is on like instrumentation, like making the things that will building the things that will make you things, or mostly things are manufactured for you and you do the experiment? Like, is it like is it 50-50? You have to make the instruments too?
Yeah, so sometimes I feel like I pick a project because I get to build the instrument. So it's mostly me building my own stuff. I don't think like any of these. Yeah, I'm looking like my instrumentation is right there. It's all built, like it's all like, I mean, of course, a lot of the parts are just like that I'm putting together. So it'll be like, I'm not making the camera or anything, or the motion axes, but I'm kind of putting it together in a way to study my specific system. So
I
the
see.
fancy Lego.
Yeah, because a lot of like advanced scientific research instruments have like extremely high precision, so it's really difficult to make in house per se, right? A lot of let's say the optics people, the laser people, most of the time they have to order in lasers or these optical instruments because they require a lot of precision. So in your field of work, is it how much precision do you need? Like, can you, when you said you make a lot of instruments in house, like what if do you need that much higher precision, or the one you have is good enough?
So it has to be kind of a combination, right? So we can use some tricks to get around having to, have the fanciest equipment. Sometimes you just need, so for example, if we need to reduce vibration, right? There's not really too much of an alternative to like a big optical table and, active isolation. So like for that, you need to just buy like we don't have time to like develop this thing, right? So you just have to buy it. But for example, like for measuring really, really tiny forces, right? I don't know if there's some commercial instrument available or not, but what we can do is we can take this tiny fiber, right? It acts like a spring. This is a big rod. So if you stick that into your droplet, now if there's a force on the droplet, you can sense that force down to um, you know, piconewtons or very, very, very tiny forces. Because and it's not like a instrument that you could buy, right? It's just you have to come up with it, and it's not that like we've come up with a way of making them, but it's not like it requires, like hundreds of thousands of dollars of equipment. It's just kind of like a workaround type thing.
And a lot of time, the principles behind those instruments are pretty simple, right? You realize like, oh, right, you just change the tiny bit of electric field or magnetic field or whatnot. I see. So I think it's in your case works pretty well.
So for the sake of time, I think we're gonna pivot a little bit, and I'm gonna ask you what got you into this. So like even in like high school before you did university, or even if you were a kid or middle school, high school, elementary school, what got you into science? Were you we always ask our guests this, and some of them kind of just fumbled their way there. Some of them like I don't want to say fumbled, but like they just kind of went with the flow and ended up there. Some of them always knew since they were 5 that they wanted to study the universe. It's some people did something else and then suddenly decided like, oh, I really like physics or science or whatever. So what got you into science as far as you can remember?
So I mean, I've always been a curious kid, so like always asking my parents a bunch of questions and trying to figure out how everything worked and building things. So I feel like science was kind of regardless, I was going into some kind of science or engineering or something like that. Just how uh, it was gonna go, and then like physics, I really enjoyed kind of like you're kind of like zooming in onto okay, this is like the 3 parameters or 3 like little things that we can actually fully understand, at least from like when we were studying in high school or even I mean I did physics and chemistry as a joint major. So it is like when you're doing your first year physics, okay, you apply a force, it moves, and so you can kind of fully understand. Well, what I thought was fully understand the system. Whereas with a biology, I still enjoy doing it, but it's a lot of it's so complicated that like it's hard to wrap your head around. You have to kind of work around the margins.
Yeah, as physicists, we're used to like isolating things, and I call them, well, I call them this based on what some other people in the world call them, but I call them minimal models, where you like, then it's another way to say toy model. It's like biology, and things get so complicated that you can't. It's hard to just describe something with a few key parameters, but in physics, that's kind of the point. Is you want to take out all the background stuff and really understand what's going on a fundamental level, and then like the background stuff comes back in and it alters it a little bit, but like overall it's that kind of that minimal model that's making things work the way it does. So did you ever, oh sorry.
Yeah, I guess our scaling models are those. They're the minimal toy models to try to.
Yeah, and then the more realistic, like the real world effects come in and alter it a little bit, but overall it's the scaling is mostly there. So I know that you're into outreach. I forget how much you are, but you're interested in that kind of stuff. Did that ever have like an influence on you when you were younger, or did you just kind of like get into it when you were older? And outreach is such a broad word, like it could mean a bunch of things, but
Yeah, so we had some experience with outreach. So, for example, there's our university. So I'm from Peterborough, so Trent. They had a sort of day or a couple of days, kind of like a little camp where you'd come in, and for example, like one of the experiments was like you'd extract some of your own DNA, and they're you extract your DNA, and then they'll do some kind of sequencing on it, and then send you a result, which you didn't really like what's going on here. But it was a fun little experiment. That had like other little experiments you do on different like physics and chemistry and different topics. So that was one of my, so as a kid, experience was outreach. There wasn't too many, like we didn't have like guest scientists come into our um, class or anything. But yeah, that was my outreach experience like as a kid. But then in grad school, the main thing was let's talk science, which I'm still doing as a volunteer.
I've never done that. So what is that? Just quickly.
Yeah, so the idea is so a teacher would request a visit from Let's Talk Science on, I want you to talk about some physics concept, or I want this specific activity. So they have access to these like different activities, kind of hands-on activities for science, and then the coordinators would take that in. So a couple years ago, for a few years, I was a coordinator for Let's Talk Science. So like you'd like organize, okay, the educators want these activities. Now let's find volunteers that can go to the schools and run those activities and make sure they have all the materials they need and everything like that. And then the volunteers go into the school and then run the activity. Now, at least my philosophy on these activities is the purpose is not to teach anyone anything, right? That's what the teachers are there for. It's just to make it fun, right? So try to make it more exciting for the students. So we just go in there and try to have a hands-on fun activity where they can do something.
I mean, physics has the reputation of being difficult and not very enjoyable, and it's kind of, it's hard to tell or sometimes because like we are doing this and we like it. For me at first I was I wasn't really able to understand why it was so frustrating for people to do physics. Sometimes like let's say someone is really good at playing piano. It's like, well, I was like, why can't other people play piano? It's like it's so much fun, right? And to be able to make something that appears scary, fun, or approachable, I think that's a big thing that we should try to do more.
Yeah, I feel like a lot people are discouraged because they think it's somehow more it's like difficult or but like you just I mean it can be difficult like anything else, but it's not like physics is fundamentally more difficult to go into than any other field. And if you can show them that early on, hopefully, at least that even if they don't go into physics, they don't hear physics.
Yes, show them chemistry is as difficult too. Look at how all these complex reactions. Do you want to go to chemistry or physics? Hey, we can reduce down to this one a tiny teeny model that if you know the force, you can cover everything. You don't need to memorize all these chemical elements. You just do the math.
That's part of it, though, is math, right? Like, people do not like math. It's always we've said this before, right? But someone asks me what I do, and I'm like, oh, I'm a physicist. The first thing they ever say is, oh, I was really bad at physics, or I was really bad at math. It's one of these weird things that people cannot tell you fast enough how much they struggled with it, which is weird because you don't usually try and admit to people as fast as you can that you're bad at something. Like someone's like, oh, I like playing basketball. You're never like, wow, I'm awful at basketball. Like you're like, oh yeah, like basketball's fun. I don't know. It's weird. So there's a lot of people like Hamza here, and who put I think people are starting to realize that we need to do more of this kind of stuff, to get people into it, or else it's not as sustainable, I guess.
I feel like the media, like the sort of media around physics being, it's like, Einstein's really, really smart and, you have to be really, really smart to get into physics, but like,
Yeah.
It-
Well,
it's just not.
if every
I think
physicist was an Einstein, I think we'd have no, I don't want to say perfect society, but we'd have made a lot more leaps and bounds, maybe.
yeah,
in
but
physics.
society would be extremely socially awkward.
Yeah, everybody would be dating their cousin.
Oh, wait, let's not go there. But
well,
well,
oh yeah,
the one thing that I noticed, like astronomers are doing amazing job at outreach more than I think any other fields I find. Like there's all usually there are astronomers that go to do the lot of outreach.
that's very true at MacMaster as well, and something that's very noticeable. Like even my supervisor, I've had conversations with him about it, about how the astronomers at MacMaster, they're so good at outreach, and I don't know if that's. I feel like I don't want to say it's easier, but I think it's a bit easier to do outreach for astronomy because you can like point telescopes in the sky and you can see things and everything looks really nice. Try and do outreach for like these people, like condensed matter guys, like, oh, I study Fermi liquids. It's like, well, what's a Fermi liquid? Like, you show someone you try and do these more like hardcore theory things, especially hardcore theory things, but like even non-theory things. Once you start getting into like relativity and quantum mechanics, it becomes harder to like do these really nice demonstrations because everything's in these really complicated experimental setups with 100 like lasers and all these weird like the breadboards and the optical tables, and it looks really cool, but it's hard to understand. Whereas like I can just point a telescope at Jupiter and be like, wow, there's Jupiter's rings. And that's I don't know what outreach the astronomers do. It's probably way more sophisticated than I'm making it out to be. But
It's really not, right? Like, just try to show the public was there. And also, like, maybe I should tap into the hippie market and just go like, hey, crystals, healing properties,
oh geez,
which is not true, by the way. Anyways, I want to go back to Hamza, and I think this is the question that we always ask our guests. We heard a little bit about from you that you want to go into industry, but I want to hear more on the general sense, or more holistic sense. Like, what are your hopes and dreams? Like, who you see yourself being? I'm not talking about timeline. It doesn't matter if it's 10 years, 20 years. You see yourself being, like, say, a research scientist for a corporation, or you see yourself coming back to teach? Like, what are your hopes and dreams?
Yes, it's a large question, but the I mean, I love what I'm doing right now. Essentially, if I could do something vaguely similar to what I'm doing right now, but get paid,
more. Yeah, I think we're all in that. A lot of us are in that boat too.
yeah. So, but I do like, I find enjoyment in a lot of different sort of pursuits. If I'm like, just like my mind's kind of like working and it's challenged, I'm not that sort of picky on the specific job I'm doing. Um, the one thing that is difficult is that I want to stay in the area possible, which like temporarily I'm maybe going to the US or something, but I want to, because I want to come back here, and there's not as many research jobs, unfortunately, in Canada as there are in the US. So that's the main challenge I think is going to be trying to figure out.
Maybe if you're lucky, you can just like hop across the border a little bit and get that American pay, but be like only a couple hours from here or something. Who knows? So usually that's the last question we ask, but I completely forgot to ask about your Veritasium experience. So Veritasium is this really popular YouTube channel that does physics and science outreach or communication. We talk about them all the time because half of what even my whole like intro topic, that kind of blurb on the great physics, I just watched the Veritasium YouTube video, right? And that's where I kind of like, oh, it's a wavelength of a microwave oven. It's 12 centimeters roughly. It's like just, from that video because he does such a good job of explaining things. So what was it? What was that experience like? And how does it feel to be on a YouTube video with 19 million views? I'm on a couple YouTube videos for like bagpiping things, but like they might have at max like 1,000 views or something like that.
Excuse me, so you're in like 90 something episode of the Hyperthesis on YouTube. Don't forget.
Oh yeah, you're right. You're right. With all 5 of our views, we love you 5 guys and girls out there listening.
Yeah. So yeah, the Veritasium. So he's a physics PhD by training, so it was very kind of easy to work with him in terms of didn't take too much explanation for him to understand what was going on, and the process is like there's like a embargo period on the paper, so there isn't as much of a like crazy rush or anything to get anything out. So the way it works, essentially, he just contacted my supervisor who was on vacation, which gave me the opportunity to do the interview instead. So he contacted me, and then essentially we had this kind of Zoom type interview where he asked me, questions about the research, some of the specific physics, but also just generally how the research came about, things like that, and then we went from there. In terms of like the response, I feel like most noticeable, like my little cousins always are more interested in the YouTube views and
what the actual video talks about, maybe. Yeah, it's a really good video. I would highly recommend watching it. I remember when we were in our undergrad and that guy came and gave a talk. It might have been before that video
It was
it was
after.
that video was after for sure, I think. And
No, the talk was after.
really?
Yep.
Okay.
So
Okay.
so the video would have been like the paper's published, the video is published. So the way it works is like there's like a week where like journalists had time to like come up with stories, and then once the paper is released, those videos can like kind of be in sync with it, so that like they aren't scrambling
Yeah.
essentially.
And the video was released 5 or 6 years ago, according to YouTube.
Yeah.
So that's why I was saying like maybe it was after that talk at St. FX. But anyway, that doesn't matter. What matters is that it's a good video and it'll supplement this episode of the podcast for sure. You'll actually get to see in pictures what we were talking about earlier. Yeah, so really cool that you got to do that. Thanks for coming again. This was a great talk. But before we end the episode with our story, we'll get Patrick to tell people how to reach us and you as well.
Absolutely. So if you are interested in reaching out and also being a guest on this episode, we were very fortunate to have Hamza here today to speak about a whole host of things, which is always exciting. And if you're an expert in your field or fields, whatever you're researching or looking into in the sciences, we would love to have you on the show. So if you want to contact us, you can email us. We are hyperthesispodcast@gmail.com. You can find that in the details below. You can send us an email. Also, if you have questions. So if you're curious about a topic, if you have suggestions for a topic, please let us know. We've talked about several topics that have been suggested through different means, and we are always excited to have new topics to discuss and learn about. You can also reach out to us on Instagram. We are at the Hyperthesis. You can like our posts. You can follow us. You can send us a DM. If you're hip and into the times and have Instagram, you can certainly reach us that way. I don't have Instagram, so I'm therefore not hip. If you are interested in contacting Hamza with questions about his research, you can contact him directly. So that can be through email, and that is Khattak at MacMaster.ca. That is also in the description down below, but that's KHATTAHK, which I'm realizing is a palindrome. That's actually really cool. So feel free to reach out to Hamza with any questions that you might have. Now, if you're listening to us, congratulations, you have found us, whether through pure luck or someone shared or you've seen something or you're a long-term subscriber. Thank you. Thank you for listening to us. We have almost 100 episodes. We are getting very close. So we have a big backlog you can listen to. There's a couple links to different episodes in the notes as well. So we are found on whatever podcasting platform you may listen to, including Audible, YouTube Music, Apple Podcast. You can also find us on YouTube. And we do have, as of the time of recording, 2,243 total views and 38 subscribers. So not too bad. More than just a couple dozen views.
We're not in it for like views and stuff, right? No. So that's just like a little bonus, I guess.
Absolutely. But yeah, so if you'd like to contact us, if you have questions for us or comments, feel free to reach out through whatever means are easiest to you. And for Hamza, feel free to reach out to him through email. And again, if you're interested in being a guest on the show, please let us know.
Nice. Thanks for having me. It's fun. Or is there another thing?
So today's story, it will focus on a couple ideas that we've touched on today. And it's based on the history of fluid mechanics and fluid dynamics. So the idea of how water flows and how fluids flow has been discussed and considered for millennia at this point. Many ancient civilizations reined in the flow of water, whether through the use of dams to hold it back or the use of different canals and aqueducts to irrigate lands, like the Mesopotamians did, which were one of the first civilizations to really settle into agriculture and irrigation. And you've probably heard of ancient Roman aqueducts that still stand today. Or you've definitely heard of the country called the Netherlands, which is reining back the sea and taking land from it decently aggressively. And there are some fun jokes about that. Now, all of these consider fluid dynamics in some way or another, and it's a field that relies on experiments historically. And many famous philosophers and scientists have had their hands in it to try and figure out how we can actually characterize the flow of fluids. When I floated this idea earlier, there were jokes about finding the best way to drink a beer quickly, which doesn't really apply to too many of these discoveries, but you might learn something about how to get some sort of beverage into your throat faster based on the size of your throat and some other things.
The vortex method.
Now, before we delve into all of that, we'll start at the very beginning and all the considerations that were taken to account for fluids flowing, especially by people who existed millennia ago, tens of thousands of years in some cases. So we see the shapes of arrows because the arrows have to travel through the fluid of air in order to hit their target, and how arrowheads were shaped in a way that makes them flow easier and straighter. And then we also see these canal systems and irrigation systems that were developed by ancient civilizations in an effort to redirect the flow of rivers and irrigate their land and prevent flooding. And truly trying to understand how fluids flow, on Earth at least, is almost instinctual to a lot of people. So you understand that water will fall and it will flow in certain ways, and will create a meniscus on top of, say, a coin when you drop it on very slowly. And this intuition kind of leads to some of the oldest experiments on Earth and how we understand the flow of fluid. Now, in ancient China, moving a bit forward in time from these super ancient civilizations in antiquity, there were observations that were recorded made on buoyancy, notably by Mencius, that compared the weight of gold to feathers. And if you haven't seen the meme about comparing the kilogram of feathers to a kilogram of steel, you should definitely check that out. And then also by Cao Chong, who described how to weigh an elephant based on displacements of boats carrying different weights. So this was theoretical, of course. There's no proof that he actually weighed an elephant, but these ideas were developed in almost synchronicity with the ancient Greeks. So these ideas of displacement and weighing objects using how things float on water was described multiple different times by multiple different civilizations. Going to the ancient Greeks, they used water to keep time, and they had a good understanding of how water flows under gravity. And again, that kind of intuition of, okay, if I make a bigger hole at the bottom of the pot, the water will flow out faster. Now, a lot of these ideas were expanded on and written down by Archimedes of Syracuse, especially in his work called On Floating Bodies. Now, his writings outline the principles of hydrostatics and dynamics. He's credited with developing Archimedes' principle, which states that a body submerged in fluid experiences a buoyant force equal to the weight of the fluid displaced. So don't do this at home unless you really want to pay some big bills, but fill up your bathtub all the way. Go ahead and hop in, submerge yourself underwater, try and collect all the water that spills over. And that's the amount of force that was, or that's the amount of volume in which you take up. So you can easily measure volumes. Now, there's a lot to be said about Archimedes, and there's a really great episode of Our Fake History, which goes over the myths and legends around Archimedes and kind of debunks him. So I would highly recommend listening to that because it goes into some of his, I would say myths they are at this point, of like going into the baths and then running through the streets naked shouting Eureka. So we wouldn't delve too much into him because there's a lot of history of fluid dynamics. But still with the ancient Greeks, we can look at the Ptolemies, who established the Alexandrian school, and the people within this focused on hydraulics, where items like the siphon, the forcing pump, and fountain compression were all invented. Now, something like a siphon, that's pretty easy if you've had to try and get water from one bucket to another, for example. to put the empty bucket lower than the raised bucket, and then water will continuously flow until the first bucket is empty. But something like a forcing pump was a lot more complicated, and it's still in use today. Now, the forcing pump itself may be inspired by the work done by certain Egyptians, but moving away from ancient Greece to a different part of the Mediterranean, we can look at the work of Sextus Julius Frontinus, who explored more closely how fluids move exactly. He was interested in this because he was a fountain inspector in Rome, which is quite the title. I think that'd be an interesting job. But he explored how water moves and is released through pipes, along with how it's distributed when it leaves a pipe. He explored ideas relating to aqueducts and fountains, which of course he was interested in. And notably, he discussed that there's some sort of relationship that exists between how water flows, the orifice size that the water comes out of, and the level of water in a reservoir. Now, of course, the math wasn't there to describe this mathematically, but he was one the first to note this relationship in particular. Now, a little bit later, turning to the Middle East, in the Middle Ages, there were a few notable Islamic scientists, particularly Abu Rayyan Biruni and Al-Khazini, who we have definitely mentioned before, who all focused on how the weights of liquids could be measured. So Biruni invented a device to determine the ratio between the weight of a substance and its water displacement, so you could actually figure out the weight of objects. And Al-Khazini invented a hydrostatic balance, so you could actually figure out the weight of things using this type of balance. Later on, the Banu Musa brothers invented a two-step level control for fluids, which was this kind of discrete fluid controller, which, again, these ideas are still used today in these types of devices. They also describe different types of valves, such as the float valve, which is used in most toilets. And Al-Jaziri, another Islamic scientist / engineer, he had a book with an excellent title of Book of Knowledge of Ingenious Mechanical Devices, where he discusses pumps in parts of it. And he most likely invented a crankshaft in a chain pump, and also discussed how the efficiency of these types of pumps can be maximized. Again, these things are still used today, including his invention of a twin piston suction pump. So he was actually able to invent a pump which was able to suck water. Now, moving back to Europe and the Renaissance, Da Vinci is well known for a lot of his work, but he did have a hand in fluid dynamics, including studying hydraulic jumps, eddy formation, tides, jets, and drag. And he is credited with developing low drag and high drag configurations for things. So think high drag a parachute, low drag something like an arrow. And this still built on intuition that's been around for millennia. He also made important steps in looking at the actual physics and discussed the conservation of mass in a 1D flow or a one-dimensional flow. Now, these basic concepts start to be expanded on more and more and more. And we have Pascal to thank for kind of bringing the entire field more into science. We can also look at the work by the Flemish engineer and mathematician Simon Stevin, who wrote the book Principles on the Weight of Water. And then also the work of Galileo, who had a hand in fluid dynamics as well. And he had two notable disciples, students, followers, who made some big strides. The first is Castelli, who explained several phenomena of the flow of fluid of waters in rivers and canals, but incorrectly assumed that the velocity of water when coming out of an orifice, say at the bottom of a bin or a reservoir, was the velocity was directly related to the height of the water above the orifice. Now, Torricelli, who you may have heard of, was another follower of Galileo's work and corrected this by saying that the speed was proportional to the square root instead of directly proportional. And this was actually confirmed by experiments. Now, you'll see throughout here that experiments are very common in fluid dynamics and really required up until towards the end of the 20th century, just because computational power was not there to simulate fluids. Now, moving on in time again, we can look to France and Marriott, who pointed out discrepancies between theory and experiments, especially on the flow of fluids, and highlighted the need for friction. So he noticed that the flow of fluids was not fully explained by theory, and so he needed to find a way in which, say, fluid flowing through a pipe wasn't flowing quite as fast as theory predicted. And so this was expanded on by Guglielmini, who observed disturbances in canals, which he said, oh yeah, it's just because of irregularities. But Marriott observed the same irregularities within a smooth glass pipe, and he suggested that each water strand experienced friction from the walls, and this idea of the water strand is expanded on later. But this friction slowed the velocity of the water, so it didn't move as quickly through pipes. Now, much like Galileo, Newton had a hand in pretty much anything physics and math related. So in his Principia, he showed that the layers within a vortex, so if you think of some sort of whirlpool or swirling water, they can actually be described mathematically. And Pitot, a French engineer, expanded on these ideas to demonstrate that slowing of water through a pipe is inversely proportional to the pipe diameter. So essentially this says the bigger the pipe, the less the slowing. Now, Newton also expanded on theoretical explanation of water discharging from an orifice, and he further refined the equations developed by Torricelli. Now, we wouldn't delve much into Newton's work with waves, but they're also a pretty big component of fluid dynamics. Moving on to a little bit more modern times, we look at the work of Bernoulli, who, if you've ever heard of a description of how an airplane flies, you've heard the name Bernoulli. And he published his theory relating to the movement of fluids. His first idea was that the level of a fluid in an emptying vessel remains level, and the horizontal strata, so if you divided that fluid into just horizontal flat sheets throughout the volume of it, said that they don't mix, so they remain contiguous. Now, this idea was challenged by Jean-Laurent D'Alembert, who formulated a principle for these dynamics that simplified the laws of motion through a very distinct calculus of what was happening. And so what he did was he took into account the motion of fluid through a little parcel, or through a little rectangle, and looked at how fluid flows out, how it flows in, and the loss of motion within that. And so he looked at both incompressible and elastic fluids, and these ideas are still used today, which we'll discuss very soon. The other concept of Bernoulli's principle is that faster moving fluid will be at a lower pressure, which again is a suggestion for how airplanes fly, but is also related to how any fluid flows. Now, theories start moving very quickly. Dubois suggested that water's viscosity and friction from any sort of channel that's traveling through counterbalances its continuous acceleration, meaning that it just reaches a steady state velocity instead of just always increasing in speed, like an object rolling down a hill. This, of course, required new experiments, and he was able to use different slopes and channel sizes, and this overall contributed to the Navier-Stokes equation, which was developed by Navier and Stokes, which is the foundation for modern fluid mechanics. Other big names in the field of fluid dynamics include Helmholtz, who helped describe vorticity, Edelwin, who described the efficiency of water wheels, which is still used today in a lot of power generation, and there were many, many others who reviewed and commented and refined on experiments. Now, moving into the 20th century, the exploration of vortices was explored more, and the idea of viscosity and the properties of a fluid were taken into account more and more. Pantel contributed to fluid dynamics with his boundary layer theory, and this was the idea that there's this boundary layer formed in a fluid next to a solid surface, and this expanded on Bernoulli's principle and Euler's equations and really showed good agreements. Now, later on in the 20th century, fluid flows could actually start to be simulated instead of just through experiments, but through computers. And we could actually construct models that supported or contrasted theories and experiments and try to replicate what was going on in the real world, but through a computer model. So this includes the exploration of waves and vortices, allowing for both examinations of small systems and large-scale systems, for example, the oceans. Go listen to our episode with Teo Weiss-Gibbons about modeling the ocean and the fluid flow within there. But this allowed us to more accurately model fluid flows, and with this, we can model anything from plasmas in the ocean to the atmosphere and even the structures of stars and interstellar gases. So overall, there's a lot of cool work going on in fluid dynamics, a lot of experiments still, a lot of computation. It's really kind of the perfect mix of all types of physics. And I think Liam said earlier that if you don't do stat mech, then you're doing fluid mechanics of some sort, which I mean is kind of true.
Careful.
So, well, it is a cool topic. I was fortunate enough a couple of years ago to take a class on waves and stability, and it's, I mean, just what can be described by simple equations is phenomenal. So fluids are ever present in our lives, from flames and fire to the ocean that makes us, and even the water in grapes. And it still remains a complicated field. But next time you see a tap running or a river flowing, just take a second and admire the complexity behind it.
Well, thank you very much for that, Patrick. Yeah, I'm a big fan of fluid mechanics, but for the sake of time, let's end the episode. So thanks for joining us again, Hamza. It was great to have you.
Yeah,
thank
thanks
you.
so much for having me.
All right.
Yeah, thank you.
We'll see everyone in the next one. Bye.
Bye, everyone.
All right, take care.